right, thanks. So I'm going to talk about something not completely unrelated. I'm going to ask sort of a basic question in economics, but I'm going to ask it through the lens of learning theory. So when do prices coordinate markets? And this is joint work with my excellent colleagues at Penn, and Jamie's making a cameo.
Also a colleague at Penn.
Yes, but you're the only one making the cameo. So I want to just sort of reflect for a moment on a remarkable fact that we all reflect on a lot. Prices are really remarkable objects because markets are decentralized, and nevertheless, prices serve as a summary statistic. We all go out, we interact with the world through prices, we optimize our own individual utility functions, we buy what we like given the prices, and by and large, things seem to work out pretty well. Markets clear, supply is approximately equal to demand, and the resulting allocation is pretty good. Okay. So let's just sort of think for a moment about what the theory tells us about why this might be in a discrete allocation problem. Okay. So I want to talk about a particular, simple object, a commodity market, which I'm going to think of as k types of indivisible goods, each of which has some supply. Okay. And there's going to be a set of buyers, and each is going to have some valuation function which maps bundles of goods to a real number, how much they like that good. Okay, and an allocation is just a function mapping buyers to some bundle of goods. Now, when facing prices, what are people going to do? Well, sort of a minimal kind of assumption is that they're going to be self-interested, and they're going to buy something in their demand set. Okay, the demand set of a buyer at some price P is just the set of bundles that maximizes his value for the bundle minus the price he'd have to pay to buy it. Okay, and there might be ties. There might be many things in the demand set of a buyer at a particular price vector, and I'm not going to assume anything about how buyers are going to break ties, just that they'll buy something in their demand set. Okay, so a classic, pricing object in this world is a Walrasian equilibrium. So just to remind us what that is, a set of prices in this setting form a Walrasian equilibrium if they can be paired with some allocation that satisfies the following three properties. Okay, so first, every buyer should be allocated something that is in his demand set. It should be some most demanded bundle of goods given the prices. And the allocation should actually be feasible. That is, the number of copies of each good that are allocated should not exceed the supply. And finally, the only case in which the number of copies of a good that are allocated that can be strictly less than the supply, the only time that can happen is if the price of the good is zero. If those three conditions are satisfied, then we can say that the price vector, together with this allocation, form a Walrasian equilibrium. And these are remarkable objects. So again, to remind you of how remarkable these are, what the first welfare theorem tells us is if such an object exists, even though a Walrasian equilibrium is sort of defined as individuals, buying things in their demand set, so it's optimizing their individual utilities, the resulting allocation has to be optimal. And these things do exist in a wide, relatively wide setting, at least if buyers have preferences that are in the gross substitutes class. And they're not hard to find. There's sort of natural ascending price auction dynamics like Kelso-Crawford that converge to them. Okay, and in fact, there's many such prices, but they form a lattice. But when I talk about them now, I'm going to focus on the minimal Walrasian equilibrium prices. And these are focal for a number of reasons, both because ascending price auction dynamics tend to converge to the minimal Walrasian equilibrium prices, and because in, say, for unit demand buyers, these things correspond to VCG prices. Okay.
What do you mean by minimal here?
So the prices form a lattice. So you can talk about the minimal price vector, which is coordinate-wise minimal among all Walrasian equilibrium price vectors. But it's not important. Okay. So it's tempting to look at this classical theory and summarize it as prices optimally coordinate a large class of markets. You can look at these prices, buy the stuff you want, and things work out. The welfare is optimal and supply equals demand. And what I want to focus on is two possible holes in this interpretation. And I want to see to what extent we can use the tools of learning theory to fix these holes. So one problem with this interpretation is that the prices do not necessarily coordinate the market. That is, a Walrasian equilibrium is defined as a pricing paired with an allocation, because fixing the prices, there's not necessarily a unique bundle in every buyer's demand set. And in fact, although we know there is some way for each buyer to pick some bundle in his demand set that will result in supply equaling demand and welfare being maximized, they might need to break ties in a coordinated way, in a way that the prices do not themselves coordinate. Okay, just to give you sort of a cartoon of how this can happen. Suppose we've got n buyers and n goods, and buyer I is indifferent between good I and good 1, and has value 0 for all of the other goods, for example. Okay. In this toy example, the minimal Walrasian equilibrium prices really contain very little information to coordinate the market. They're all 0. And at these prices, every buyer remains indifferent between good I and good 1. Okay, the only way to coordinate an optimal allocation is for buyer I to buy good I, but if, say, they break ties randomly, half of them will attempt to buy good 1. They'll be horrific over demand.
Since you mentioned ascending price options, this would be one way to coordinate buyers? So
yes, good. So I'll get to this. So the prices themselves here are not a coordinating signal. If you actually participate in a dynamic like Kelso-Crawford, it's true, the history of your coordination, the history of your participation in the auction serves as a coordinating device. But that'll be the second thing I'm going to get to. Okay? And I want to point out that you could come up with a distribution over instances where, say the distinguished good is chosen at random, and then any tie-breaking rule that the players used that was independent of the other buyers would result in expected over demand n over 2 for this good. And the prices here are doing very little to coordinate. Does this make sense, this example? So I forgot to mention, but the first buyer here is also an economist. And he objects. He says, okay, I mean, you can cook up examples in which coordination is a problem, but this seems non-generic. There are, lots of ties here. And what this buyer means by his objection is that perhaps if the values are drawn from a sufficiently smooth distribution, perhaps, then maybe with probability 1, there are no indifferences at the minimal Walrasian equilibrium prices. Maybe somehow we never expect to see indifferences, and this is something that can only happen if you're a computer scientist obsessed with worst-case measures. But that's not true, unfortunately. So it's not too hard to see that there will always be indifferences at the minimal Walrasian equilibrium prices. It's not too surprising. Equilibria tend to induce indifferences. But suppose there weren't. By that I mean, suppose you had a market where there were no indifferences. Okay, so what that means is that a good J is demanded by some buyer I if and only if buyer I is the one who's supposed to get good J in the optimal allocation. Well, in that case, I could take any non-zero price and I could lower it by epsilon, and I'd still have a Walrasian equilibrium, but that would contradict minimality. Okay, so whenever we've got minimal Walrasian equilibrium prices, we always have indifferences, and genericity is somehow not going to save us from this fact. Okay, now, clearly, if I'm going to tell a story in which prices alone serve to coordinate markets, we're going to need to make some kind of genericity assumption, because the example I showed you, the prices just don't coordinate the market. But what I want to point out is that we need to approach this by considering approximation. We cannot appeal to genericity simply to remove the problem altogether. Okay, so here's the second problem. So where do the prices come from? And as Ilya pointed out, we do have stories for this. There are ascending price auction dynamics that converge to these prices. And in fact, if you participate in these dynamics, they also solve the coordination problem for you. They're ascending price auctions, and the bundle of goods you're supposed to get are the last bundle you bid on. Okay? But in practice, when I walk around Berkeley, I do not participate in ascending price auctions. Somehow the prices are not a function of my direct participation. Okay? So in practice, we sort of imagine that prices must be encoding distributional information about the market. But because they're not a function of my participation, we cannot rely on sort of the history, my memory of participating in some ascending price auction to serve as the coordination device. Okay? So this also brings up questions, if we're going to assert that prices are encoding distributional information, this brings up questions of the sort that Tim just talked about. How much distributional information is necessary? How many samples do I need to see from some population before I can be confident that the prices I've got are pretty good for the distribution, not for the fixed population? And of course, in a model like this, the prices I'm using, since they weren't computed as a function of the people actually buying the goods, are only going to be sort of approximate equilibrium prices, which might just exacerbate the coordination problem. Okay, so we need some theory maybe of how approximate equilibrium prices work and are learned. So here's the model we're studying in this work. Okay, we've got a commodity market, we've got k types of goods, and each has some supply. And we've got some unknown distribution over bidder valuations. And n bidders, n buyers, are sampled IID from this distribution. And I'm going to assume that the market is going to equilibrate at the minimal Walrasian equilibrium prices computed, defined by the market, including these n bidders. I'm agnostic to how this happens. Perhaps they actually do participate in a Kelso-Crawford-like dynamic. But the important point is these prices are not going to be used to sell goods to these buyers. Instead, once the prices are fixed, a new sample of n buyers is drawn from the same distribution. And these buyers have no information to coordinate them other than their price. So at this point, the buyers are going to buy arbitrary bundles in their demand set, given the prices. I'm going to assume nothing about how ties are broken. It could be worst case. And the question is, well, how much overdemand do we expect? And what kind of welfare do we expect in the resulting allocation? And what do these things depend on? Do they depend on the particulars of the distribution? Do they depend on somehow the complexity of buyer valuation functions, or the number of buyers, or the number of goods? Okay. And to answer this question, sort of taking the perspective of learning theory, there's really two separate questions I need to answer. The first is, when do the exact equilibrium prices induce little overdemand on the market for which they were computed? And by analogy to machine learning, this is asking, when is the training error small? When can I expect low overdemand for the prices fit specifically to a market? And remember, from the example I showed you, the answer is not always. We'll need some genericity condition, and we'll need to talk about it in terms of approximation. And the second question is, how well do equilibrium prices that are computed on a particular sample generalize to new buyers drawn from the same distribution? And again, by analogy to learning theory, this is the analog of generalization error. Okay? And how much data is needed? So let's think about the first question. And for the purposes of the talk, let me tell you just about unit demand buyers, although in the paper, and I'll mention at the end, we actually handle essentially up to gross substitutes. Okay, but unit demand buyers are real simple. They just want one item, and therefore their valuation functions can be described. Each buyer just has sort of k real numbers describing his valuation function, how much he likes each good. And the genericity condition we're going to ask for here, in this case, is also extremely simple. And it's essentially going to say that these numbers, which specify the valuations of the bidders, should be linearly independent over the integers. Meaning, if I take some linear combination of these numbers with integer coefficients, and the linear combination sums to 0, the only way that can happen is if all of the coefficients are 0. And I don't even need linear combinations over the integers. It suffices to have this where the coefficients can be -1, 0, and 1. That's the genericity condition I'm going to ask for. Remember, we need some condition if overdemand is going to be low. And just a note on this assumption, it does imply that the welfare optimal allocation is unique. And that's important because if there are multiple optimal allocations, they will all be supported by any equilibrium price vector, and so you'll get indifferences. And it's satisfied with probability 1 for any continuous perturbation of the valuations. So maybe I'm justified in calling it a genericity assumption. Okay, and the theorem in this simple case is that if we've got valuations that satisfy this genericity assumption, and we've got the exact minimal Walrasian equilibrium prices on this market that is computed with respect to the actual bidders, then although there will be some overdemand, it will be as low as possible. And the number of people who demand each good will be no more than one more than the supply of the good. In particular, no matter how people break ties, with no assumptions on how they break ties, although there will be indifferences, the overdemand on any good will be at most 1, and therefore it will become a diminishing fraction of the total supply as the supply grows large. Okay, so the proof for unit demand is simple enough to show you. So let's fix the optimal allocation, which is unique, and fix the minimal Walrasian equilibrium prices. And I want to think about a graph. Okay, the vertices are going to correspond to the goods, so there's k vertices. And there will be an edge between good j and good j prime if there's some buyer I who is assigned in the optimal allocation good j, but who also has good j prime in his demand set. So the edges represent indifferences. Okay, so we've got a graph like this. The vertices are goods, the edges are buyers. And the first, I just want to make a series of simple observations about this graph. The first observation is the graph has to be acyclic. Because if it's not, players could swap allocations around a cycle. They'd all still be getting a most demanded good. The supply would still equal demand. And by the first welfare theorem, this would be a different optimal allocation, which would contradict the uniqueness of the optimal allocation. Okay, so the graph didn't look like this. That edge wasn't there. The graph has to be acyclic. And since the graph is acyclic, I might as well topologically sort it and rename the vertices in order. Okay. And the first vertex is going to have in degree 0 since it's a topological sort. And the next observation is any good that has in degree 0, and we know there's at least one of them, has to have price 0. And that's not too hard to see. If it didn't, I could just lower the price by a little bit, and I'd still have Walrasian equilibrium prices, which would contradict minimality, because there's nobody who isn't getting the good but is indifferent to it. Okay. So anything with in degree 0 has price 0. And so I claim any price in the minimal Walrasian price vector can be written as a linear combination of buyer valuations where these are valuations for goods that come earlier in the topological sort than good j does. Okay. The base case is, well, if the price is 0, then we're done. And if the price is not 0, remember, we know it's got to have in degree at least 1. Okay, so if the price is bigger than 0, there's some buyer I who's receiving a good in the optimal allocation earlier in the ordering, but is indifferent between that good and good j. Okay? And we can write down that indifference condition. His value minus price for the good he's receiving is equal to his value minus price for good j. That's what it means for him to be indifferent. And just rewriting this, we can write good j as a function of his value for these two goods plus the price of good j prime, and just apply our inductive assumption to the price of good j prime, which is earlier in the ordering. Okay, and so we're almost done. The final claim, which is what we want to prove in the end, is that all goods in this graph have in degree at most 1. Or the in degree of the graph represents the demand of the good beyond its supply. And suppose not. Suppose there was some good that had in degree 2. Then there are two buyers, I and I prime, who are both indifferent to this good and some good earlier in the ordering. Okay? So we've got two different indifference conditions, but both of them have the price of good j in them. So we can just solve for these two different expressions for the price of good j and subtract them from one another. They equal 0. Okay, but we're going to get a linear combination of valuations that violates our genericity condition. So that's it. Okay. So remember, this was sort of step 1 of the argument. This was the analog of asking for a condition under which training error was small, but we've got to talk about generalization error as well. Oh, and let me just mention that the proof is very simple. That's what I showed you for unit demand valuations, but our result is not limited to that. So we've got a similar genericity condition and a substantially more complicated argument. It's good to have graduate students. That guarantees the same result, maximum over demand at most 1. For the class of what are called matroid-based valuations, these are a class of valuations that has some nice structure you can work with to talk about this indifference graph, and in fact is conjecture. These valuations are a subset of gross substitute valuations, and it's in fact conjectured but to be equal to gross substitutes. Okay, so modulo this unproven conjecture that matroid-based valuations are equal to gross substitutes valuations, the result is fully general in the sense that it holds for the largest class of valuation functions for which Walrasian equilibrium prices are guaranteed to exist. Okay, so let's sort of tackle the second question now. Okay, we've got some condition under which exact equilibrium prices, when computed on a population, induce low overdemand. That's pretty good. That means we can at least fit good prices to a sample if we get to compute the prices as a function of that sample. But we also need to ask, how well will these prices generalize in terms of both overdemand and welfare if we use the same prices on a new population? Okay, so and now we're going to get a little bit closer to Tim's talk. We're going to have to talk about uniform convergence over some class of functions. And the question is, what class of functions do we want to talk about? So let's define some functions. Okay. Fix some tie-breaking rule. It can be arbitrary, but fix a tie-breaking rule that the players are going to use, and maybe it can even be different for every player, to select bundles in their demand set when their demand set is not unique. And I just want to give a name to the bundle that buyer I will select facing prices P according to this tie-breaking rule when he faces prices P, which bundle in the demand set he'll buy. Okay.
Sorry, that's a deterministic thing over there?
Let's say it's deterministic. Nothing particularly changes if it's a randomized rule. But let's say it's deterministic. Okay. And I just want to use this to define a function. Okay, fixing prices P. Let me define this function, parameterized by P, to be the function that takes as input a valuation function VI, and just tells me what bundle of goods a buyer with valuation VI is going to attempt to buy when he faces prices P. Okay, I'm just defining the function. And, okay, so the range of this function is bundles. And now let me define sort of a one-dimensional projection of this function. I'll call it D for demand. And it's going to be parameterized both by a price vector and by a good J. And what it's going to tell me is, given as input a valuation function, will a buyer with valuation function VI buy good J or not? Okay, this function takes value 1 if he will choose a bundle that has good J in it, and value 0 otherwise. And the reason this is a good function to think about is because given a distribution over valuation functions and a particular price vector I'm going to use, the expected demand for a good J, given the price is P, is just n times the expected value of this function when I evaluate the expectation over valuation functions drawn from the distribution. So it's going to suffice for us to obtain uniform convergence of the empirical averages of these functions, the class of functions which map valuation functions to the indicator of whether a buyer with that valuation function will buy a good J or not. And this class of functions is parameterized by price vectors, so the class includes sort of uncountably many functions, one for each price vector. It's going to suffice for us to obtain uniform convergence of the empirical averages over all this set of functions to their expectations. The reason is because if we can do that, then with high probability, over 2 draws of n bidders from the same distribution, we'll know that for every price vector, demand will be similar on both of these 2 samples. And in particular, since it holds for every price vector, it'll hold for the minimal Walrasian prices computed on the first sample. And subject to the genericity condition, we know that in that case the overdemand must actually be small.
Aaron?
Yeah.
So the randomness here is not over the tie-breaking rule. Like there's no new sample.
That's right. Here, for the purposes of the talk, let's assume the tie-breaking rule is deterministic. The randomness is entirely...
You said you fixed the tie-breaking rule, so you're fixing it for training and test, basically. No?
That's right. And the randomness is over the draws from the valuation function. Okay. So this sort of goes back to a question Shadden asked in Tim's talk. There's a relationship between learning and uniform convergence. Okay, it's sufficient to obtain uniform convergence. Uniform convergence is sufficient for learning, but it is not necessary when you're in a general learning setting. Okay? But it happens that if the function you're trying to learn is a one-dimensional Boolean-valued function, then the number of samples you need in order to learn, meaning the number of samples you need in order to reliably predict the outcome of a function, is exactly equal to the number of samples you need to obtain uniform convergence over the class of functions you're learning over. Okay? So the argument we make goes through the following diagram. We show that these functions f, which map valuation functions to bundle predictions, these are not Boolean learning functions, these are learnable with k over epsilon samples. This is in fact not enough to obtain uniform convergence over this class of functions. But learning these functions, the bundle predictions, is sufficient to also learn these sort of lower dimensional functions, which just ask you to predict, is a buyer going to buy good 1 or not? Because if I can accurately predict the whole bundle he's going to buy, I can also tell you if he's going to buy good 1 or not. And so I know this class of functions is also learnable with k over epsilon samples. And since that's a Boolean class of functions, k over epsilon samples is enough for uniform convergence. So I don't have much time, so I won't go through the details, but the learning result we use when we're trying to learn this function in bundle space has to do with this technique of compression bounds. It's sort of a classical technique that doesn't require uniform convergence, but isn't, I think, as well known in our community. And it turns out that using a very nice learning result by Danieli and Shalev-Schwartz that was first used, brought to our attention in an economic context by a paper of Balkan et al. And Ruta is in the audience. I don't know if any of the others are. Using this technique, you can relatively straightforwardly argue that this class of functions mapping prices to bundles is compressible. Okay? This is a really, if you haven't read this paper, you should. It's a nice class of functions from an economic context that turns out to be easily learnable. And so the result is these functions are learnable, and we get uniform convergence with only k over epsilon samples. Okay, so skipping to the punchline, the total demand for any good, in the end, on the new samples drawn from the distribution, is with high probability going to be within a 1 plus or minus epsilon factor of the supply, under the condition that the supply is larger than k, the number of types of goods, over epsilon squared. Okay, so in order for these prices to actually work well, you need the market to be somewhat large. The supply of the goods got to be, kind of big relative to the number of kinds of goods, but not, not too big. And you've got to go, that was for overdemand, you've got to go through a similar argument for welfare. Welfare doesn't allow you to do this trick of mapping onto a Boolean class of functions, because welfare is sort of real valued. You've got to directly go through some argument bounding pseudo-dimension, which I won't worry you with. But you get a similar punchline for welfare. And so I'd like to end the talk thanking our sponsors. Ricky noticed that Delta actually has an ad campaign that's remarkably similar to the title of this workshop, and so I assume this is where our sponsorship is coming from. So thank you. Yes?
You probably said this. So I apologize, but I was wondering why do you want to focus on minimum while raising prices?
So to ask these questions, you do have to fix some Walrasian price vector. I don't want you to pick among the set of Walrasian prices as a function of the actual realized valuations. That would be one way to try to coordinate people, but it would sort of be cheating. And among the set of Walrasian price vectors, I sort of view the minimal ones as being focal because that's what these ascending price dynamics converge to. But you could ask the same question for other Walrasian price vectors, and I don't know the extent to which all of these results generalize.
So suppose I pick the prices in a kind of generic way. Then does that do anything to resolve this problem?
That probably depends on what you mean, pick the prices in a generic way. Certainly, if you're allowed to pick the prices as a function of the people you're going to sell to, then it turns out that if the max welfare allocation is unique, there is a way you can pick the prices that will result in no indifferences. But somehow this is solving the coordination problem by a centralized planner who's got access to the valuation functions of the people he's actually selling to. Because you've got to compute these things as a function of the values. If you do not have access to the values of the players you're actually selling to, then I don't know any way in which you can sort of generically pick prices that will resolve this problem. But that's an interesting question.
Well, I guess that's maybe segueing from what you just said is, in those cases where your number of samples is too low for prices to work well, what would?
Yeah, good question. I mean, our results are sort of tight in that the VC dimension, the number of samples you actually need for uniform convergence is also at least the quantity I wrote down. So, you know, if the number of samples is too low, then I'm not sure exactly why you would necessarily expect these prices to coordinate the market without some extra assumption or some extra.
So your result basically matched that. That is, whenever you can learn, you can actually find a price mechanism that would achieve what you want.
Yeah, I think.
So that in itself is interesting.
Aaron, can I do a follow-up on this?
Sure.
I mean, what if you have just a little bit less sample? Like, is there a smooth deterioration here? Like you got not quite enough sample to learn it right, but maybe half as many or something?
Well, so remember when so maybe I'm misunderstanding the question, but the bound I gave was parametrized by epsilon. I said if you want to get within, 1 plus or minus epsilon factor of the supply, then you need k over epsilon squared samples. But alternatively, I can say here's the number of samples you have. I'll solve for epsilon. This is how well you do. Thank you.